Hello everyone. In this video, we will discuss our paper Strongly Topology-Preserving GNNs for brain graph super resolution. This work was done under the supervision of Dr. Islam Rakik as part of my master's project at Imperial College London and was recently accepted to the Prime MICCAI workshop. First, let's briefly discuss what a brain graph is. A brain graph is created by dividing a brain into multiple regions of interest that also act as a nodes of the graph. We then create edges between these regions where each edge represents some connectivity information such as the correlation between neuronal activity, the difference between cortical thickness, and so on and so forth. This connectivity or edge information could also be represented as a connectivity matrix, which forms the adjacency matrix of the corresponding brain graph. Our task of brain graph super resolution then corresponds to predicting a high resolution brain graph from a low resolution brain graph. This is generally done using graph neural networks. Graph neural networks are machine learning models designed to natively handle graph structured dataset by performing recursive message passing operations to update node feature vectors. At a high level, this can be seen as doing node representation learning. However, this formulation presents a limitation for edge learning task. As can be seen from this graph, in the node representation learning framework, each node feature needs to encode all the edges originating from the node. For any two nodes, such as 1 and 2, their node features will end up encoding all edges from these nodes and therefore will have limited capacity to directly model the individual edge E12. To circumvent this issue, existing graph super resolution models employ expensive node representation learning frameworks to learn complex node features capable of encoding edges. However, these models cannot be upscaled to larger graphs. Therefore, in this work, we explore how can we design an edge representation learning framework that allows us to use simpler GNNs to directly model edges. For this, we came up with our STP-GSR framework. Our STP-GSR framework consists of two modules. A target edge initializer module that learns an initial approximate value for the high resolution edges, and a dual graph learner that further refines the approximate values using a dual graph formulation to generate the final high resolution connectivity matrix. Before diving into the two modules, let's discuss what this dual graph formulation is. It is essentially equivalent to creating a unique mapping from the edges of our original graph and nodes of a newly created dual graph. For this, we start off with our original or primal graph and give a unique identifier to each node. We then map each of these edges to a unique dual node. But how do we connect these dual nodes? This is done by connecting an edge to all of its edge neighbors in the primal graph. For example, the sixth edge has 4 neighbors in the primal graph. Therefore, the corresponding dual node would be connected to nodes belonging to these 4 edges. By repeating this process for all edges, we obtain our final dual graph. Note that this mapping is invertible and any computations we perform on the dual nodes correspond naturally to edge space computations on a primal graph. Now we will move on to the individual modules in our STP-GSR framework. The first one is a target edge initializer that learns approximate edge values for the high resolution graph. Starting with the low resolution graph, we pass it through traditional node representation learning models to update the low resolution node features. We then employ a simple linear algebraic trick involving matrix multiplication to transform the low resolution node feature matrix into high resolution connectivity matrix, where each cell represents the initial edge value of the high resolution brain graph. The next module is the dual graph learner, where we refine our initial edge values to generate the final connectivity matrix. For this, we start off with our approximate high resolution graph and create the corresponding dual graph, where each dual node is assigned the initially learned edge value. We then refine these values using message passing on the dual graph using simple GNN models such as the graph transformer. Finally, we map the dual node values back to primal edge values, giving us a predicted high resolution connectivity matrix. As mentioned earlier, the objective of all these operations is to take the approximate high resolution graph and refine it in the edge space to get our final predictions. Now that we have described our framework, let's discuss how we evaluate it. We compare it against the current state-of-the-art model Imam GraphNet, which has been slightly modified for our dataset since its original formulation results in an out-of-memory error. Along with this, we also create two new baselines. In terms of evaluation measures, we calculate the loss between true and predicted graphs using 7 widely used topological measures in network neuroscience, as well as the mean absolute error between true and predicted matrix. Here are the results we obtain for the topological measures and the MAE. We observe that our model outperforms the current state of the art across all 8 evaluation measures, as well as outperforms the new baselines across all topological measures. This points to strong topology preservation properties in our framework. To conclude our work, we noted strengths and possible future research direction. In this work, we tackled the problem of edge representation learning by mapping edges to nodes of a dual graph. This allowed us to use simpler GNN architectures to directly model edges. The resulting framework showed strong topology preservation, outperforming all models across a diverse set of topological measures. Even though we achieve impressive results, the framework could be further improved by further optimizing the GNN architecture. For example, by using residual connections through better scaling methods, etc. Moreover, in line with existing work, we employ a simple linear algebraic trick to map low resolution features to high resolution connectivity matrix. However, it would be worthwhile to explore and develop other graph-based alternatives. Finally, thank you so much for your time, and do let us know if you have any comments or feedback on our work.